This video is a continuation of our discussion in VSEPR. We're going to cover three things in this video: the effect of non-bonding electrons and multiple bonds on bond angles, molecules with expanded octets, where do those extra electrons go, and then how do we predict the shapes of larger molecules. Okay, so three topics. So the first one, it says for us to consider the three molecules CH4, NH3, and H2O. So if I draw those in a Lewis structure, they're all pretty easy Lewis structures to draw. And we now know from our last lesson that we can predict the shapes of these. So from their electron domain geometries, they all have 4 electron domains. They're all going to stem from a tetrahedral arrangement. And that should give us a bond angle of 109.5 degrees. That's the bond angle in a pure tetrahedral. So if you were asked to predict the bond angle here in CH4 and NH3 and in H2O, your answer probably would be 109.5 because that is the bond angle that stems from a tetrahedral geometry. However, that's only the case with CH4. So this angle, even though it's drawn to look like 90, actually is 109.5 degrees. However, when we move to NH3, the bond angle where we expect it to be 109.5 is actually a little bit smaller. It's 107. And in water, the bond angle is even smaller, and it's about 104.5. Okay, so why? Well, the first statement we're going to make is just a bold statement that says that the bond angle decreases as lone pairs on central atom increase. We can see that pretty clearly in this example. CH4 has no lone pairs, NH3 has the 1 lone pair, and then H2O has 2, and my bond angle is decreasing in those scenarios. Okay, but the bigger issue here, of course, is the why. And so it's kind of an interesting discussion, but it's the fact that so when we have a bonding pair of electrons, okay, they're attracted to the nucleus of both atoms. Okay, so they're attracted to 2 nuclei. So like, for example, in NH3, this pair of bonding electrons, okay, is attracted to the nucleus of hydrogen. It's also attracted to the nucleus of nitrogen, okay, and that would go for any type of bonding pair of electrons. However, a non-bonding or a lone pair is only attracted to the nucleus of the atom that it's on. So in this case, the lone pair is only attracted to the nucleus of nitrogen. It has no attraction to the nuclei of the other hydrogens, okay? And so because of that, the lone pairs, or they're also called non-bonding, experience less nuclear attraction and they kind of spread out more, and that means they take up more space. Okay, so you can kind of think of it almost like as a balloon, and then if this was a balloon on the nitrogen, okay, that it's taking up more space, and then it's causing the other angles to compress a little bit, and that's why they're not exactly 109.5. So let's see, so they spread out, taking up more space, causing angles to compress. Okay, it also happens with multiple bonds. So if we were to draw, I'll just draw you this Lewis structure. I didn't leave myself a whole lot of room. I misjudged this one just a little bit. Okay, so if I were to look at this picture, this is obviously a trigonal planar shape, and that should give us, we would think that the bonds would be 120 degrees, okay, but actually it's a little bit different than that. This bond angle here is about 111, and these bond angles are about 124. Okay, so what's the deal here? Well, it's the same thing, but actually a little bit different. So the double bond or the multiple bond, so it exerts a greater repulsive force. And what that's going to do in this case is causing the single bonds to move away. Okay, so let me change my color here so I can kind of show you this. Oops. So where we think that these angles should be 120, what has happened is this whole double bond, okay, is expressing, it's not a good word, is exerting more of a repulsion than a single bond. And so what that does is it makes my single bonds kind of move away a little bit. So it's like they're almost being pushed away from that double bond just a little bit, which is going to, of course, cause this angle to get smaller because those chlorines are moving a little bit closer together. So that'll happen with a double bond. It's also going to happen with lone pairs on your central atom. So what's the takeaway here? That we're going to have some bond angle variance, okay? It's not always going to be the bond angle that you've kind of memorized due to one of two things. One, either lone pairs, or two, a multiple bond scenario. Okay, so that's the first topic that we need to talk about. The second topic is what happens when we have a molecule with an expanded valence shell? Where do we put the lone pairs? And so we're going to talk about the situation where we have 5 electron domains, which of course is the trigonal by pyramid geometry. Okay, and I'm going to try to draw this for you. So we have a central atom, and then I'm going to have, let's see, and I'm going to draw this with our like dot line wedges, so that means it's coming toward me, this one's going away from me. And I'm going to change my colors here only to try to show you something. We'll use red and, I don't know, green. Okay, so we have 2 different positions in this case, okay, and keep in mind, I guess I should go back to here. Keep in mind that we have 2 bond angles. In the trigonal bipyramid, we have a bond angle of 90, and then we have this bond angle like here that stems from a trigonal planar, so it's a bond angle of 120. It's the only shape that has the 2 bond angles in it. So, but that means now I have 2 different positions. So in this green position, okay, these are called equatorial. Oop. And the red are referred to as axial positions. Okay, and actually if you think about that, it makes sense. Like if you almost picture the black as like the earth, then the line that runs, you know, this direction is the axis. Okay, and then the line that runs this direction is the equator, right? And so that's where these names come from, the axial and the equatorial. So the question now is, what if we have one lone pair? Where does it go? Now, from learning the shapes, you and I both know that it's going to go in an equatorial position because that's what gives us that seesaw shape. Okay, but the question is why? So we already know where it goes, but why? Okay, so the answer is going to be it's going to go in the equatorial, but why is that the case? So let me show you. If I redraw my picture with my lone pair in the equatorial position, versus if I redraw my picture with my lone pair in an axial position, we're going to hope that this helps to clarify why the lone pair goes in an axial. So and this is hard to do without the model, so just kind of bear with me. But in the equatorial position, what we're looking at is the fact that this lone pair is now 90 degrees away from this atom and from this atom, okay? And it would be 120 away from this guy and this guy. So it's it's 90 degrees away from two, we'll say bonds, okay? Which of course are other electrons. Keep that in mind. Remember, these lone pairs and the electrons in a bond don't like each other, okay? So they want to be as far apart as possible. However, in this, if it's in the axial position, then that lone pair is now 90 degrees away from this one, and even though it's hard to tell, from this one. So in the axial position, it's 90 degrees away from 3 bonds. So what we're looking for here is what's the lesser of the two evils. And so because in the equatorial position, it's 90 degrees away from only 2 things, there's less repulsion. And so that is why the lone pair is going to assume an equatorial position. And then once it assumes the equatorial position, all lone pairs are going to take that same shape. So we know that stemming from a trigonal bipyramid with 1 lone pair, it's a seesaw. With 2 lone pairs, it's a T shape, because you're taking that second equatorial position, and then 3 lone pairs, you're taking the third equatorial position, which is going to leave you with a linear shape. Okay. Now, what if we talk about an octahedral? Okay. Well, an octahedral. Oop! I forgot my center. Okay, an octahedral is a perfectly symmetrical molecule. So there really are no axial or equatorial positions, because if you rotate the thing, then there's no difference. So we don't really discuss axial or equatorial here. In an octahedral, we put the lone pair somewhere. So wherever the lone pair goes, it doesn't matter, because again, it's perfectly symmetrical. It's only the second lone pair, which is going to be placed 180 degrees away from the first one. So that's why you learn that in a octahedral, for example, if we take, normally it's the bottom one. Oh man. Only because we then learn that with 1 lone pair, this is a square pyramid. And then with 2 lone pairs, right, it's always opposite, it's square planar. Okay, and so that's the way it works with the octahedral. A much simpler discussion, because the octahedral is a purely symmetric molecule, where the trigonal bipyramid molecule is not. And that's how come in a trigonal bipyramid we have this discussion of an axial versus an equatorial position. Okay, and last topic is, how do we use VSEPR to explain the shape of a larger molecule where perhaps you have more than one central atom? And you might think it's impossible to do, but it's actually not. So if we draw acetic acid, okay, acetic acid is hinting for us at the Lewis structure, because it's got a carbon with 3 H's. That's why it's written like that. Okay, and then connected to another carbon, which is going to be connected to an oxygen. The oxygen's connected to an H, and then my other oxygen is on the carbon. I have to get my electrons all correct, and it's going to be a double bond here, lone pairs. Okay, so that's my Lewis structure for acetic acid. So if I asked you about the geometry of this, you should say, I have no idea, because we've yet to talk about how we can take the discussion of VSEPR and break it down for a larger molecule. So what we're going to do is look at the geometry around each central atom. I know that sounds weird, because up until this point we've only ever said we have one central atom, but in this case we're actually going to view this carbon, and this oxygen as a central atom. Notice the other ones are all on the outside, and so we're going to talk about the geometry surrounding each of the carbons. So, you know, in the first discussion, I'm only talking about the geometry surrounding this leftmost carbon. Well, it's got 4 electron domains, and so surrounding this carbon, it would be a tetrahedral geometry. We would expect your bond angle to be 109.5. Surrounding the middle carbon, okay, it's got 1, 2, 3 electron domains, And so we would expect that to be a trigonal planar with a bond angle of approximately 120. Notice I said approximately because of this double bond. That's going to change it a little bit. And then around my oxygen, I have 1, 2, 3, and 4 electron domains, which is going to stem in a tetrahedral arrangement with bond angles of, again, approximately 109.5. We know it's going to be smaller, though, because of the compression from the lone pair. So in this case, you really can't talk about the geometry of the whole molecule because it's the geometry at each of those atoms. So I can actually draw a more realistic picture of this, and this is what it would look like. So if I do my geometry around my first carbon, it would be a tetrahedral arrangement. Okay, and then this would be the second carbon. At this carbon, it would be a trigonal planar. So it would look something like this. Oop. And then around the oxygen, actually, so it's a tetrahedral arrangement, but it's only has two lone pairs, which means it's going to be a bent structure. And then my lone pairs would be like this. So this is a much more accurate representation of what acetic acid looks like than the Lewis structure I drew to begin with. Okay. Now most of acetic acid is in fact planar. The whole up until these last two hydrogens, right? This whole thing is flat. Okay, but this part makes it not planar, and you wouldn't have known that if you just looked at this thing as a whole. So the takeaway here is that we can use VSEPR at each central atom to discuss the geometry around each of those atoms, and then giving us a clearer picture on what the geometry of the whole molecule might look like. So there's two practice problems, and they ask you to predict the bond angles. So you can pause this and try it on your own if you want, but I'm going to go right into it. So predict the values for the HOC bond angle and the OCC. So the HOC bond angle would be HOC. So what's the bond angle here? So surrounding the oxygen, it's going to stem from a tetrahedral, 4 electron domains. Going to be approximately 109.5, although it's going to be slightly less. Oops, should have gone the other way. Going to be slightly less than 109.5 because of the compression from the lone pairs. And then the OCC bond angle, so what's the geometry surrounding this central carbon? So I have 1, 2, and 3 domains. While they didn't ask for the geometry, that's of course what's going to give us the bond angle. And so that geometry should be, that bond angle should be about 120. A little bit less because of the double bond, but close enough. And then the second practice, same thing. So the HCH bond, that would be here. The geometry around this carbon. So 4 domains, tetrahedral, no lone pair. So we would expect this bond angle to be pretty exact to 109.5. And then the geometry around the carbon-carbon-carbon bond. So what's the geometry around this carbon? Well, it only has 2 electron domains, which is going to make it linear. And so we would expect a bond angle of 180 degrees. So that's how you use VSEPR to discuss the shapes of larger molecules.